Today we're going to talk about how to do summations using sigma notation. And this is going to be important, a short little topic that we need to use in order to work out some integrals before we're able to learn some bigger rules for integrals. So sigma is just this Greek letter right here. When I draw it, it's going to probably look like that. Sigma just means add up all these things. So it just means add up all of the terms from wherever we start at, which is k equals 1. So in this case, k equals 1. It could be k equals 2 or any other number, any other whole number. So when we do these summations, we're only going to be using integer values for values of k. And so the summation says start at k equals 1 and go until we get to some number n, some integer number n. And so what that means is add up all of these terms from the first one up to the nth one. So effectively, that would be term 1, a sub 1, plus then when k is 2, it'd be a sub 2 plus a sub 3, all the way up until we get to, eventually, a sub n. So if n was 10, we'd have 10 terms here. We'd add a1 plus a2 plus a3, all the way up to a10. If n was 100, we'd have 100 terms there. That's all this summation really means. So for the first one we've got down here, where we actually have a value for n, the sum from k equals 1 to 5 of k, just means add up all of the integers from 1 up to 5. So we're just doing 1 plus 2 plus 3 plus 4 plus 5. So we're adding all the k's, all the integers, from the first one to the fifth one. And so, I mean, obviously we can add those all together and get 15, but the point here being that 1 plus 2 plus 3 plus 4 plus 5 is what we are to evaluate. We have a sum from k equals 1 to 5. So in the next one, we've got the sum from k equals 1 to 5 of 8. This is a little different because we've just got a number inside that summation. So really all that means to us there is that we need to add together all the 8s from the first 8 up to the fifth 8. Well, the first 8 is 8, and the second 8 is also 8, and the third 8 is also 8, and the fourth 8 is also 8, and the fifth 8 is also 8. So effectively what this is telling us to do is it's telling us to add 8 5 times. So we've got 8 times 5, and so that's just 40. Anytime we're summing together a bunch of constants, like we have down here in this last one, the sum from k equals 1 to n of c, some constant, effectively all we're doing is we're multiplying that constant times the value of n, in this case, just n. And so we'll need this to evaluate some of our later summations when we're doing this with them. Now, there's a couple of special cases for these summations that we want to know about. That we'll need to sort of have memorized to complete a few of the problems. So here we're looking at a sum from k equals 1 to 100 of just k. So effectively, that means 1 plus 2 plus 3, all the way up to 99 and 100. And so we're going to use a quick little trick to try to find this value, because it takes us quite a bit of time to actually add up all those numbers. So what we're going to do is we're going to have another one of these, another sum from k equals 1 to 100 of k. But this time, instead of writing it in the order I've written it up there, I'm actually going to write it backwards, which is fine because addition is commutative. It can be done in any order. So I'm going to add 100 plus 99 plus 98 all the way down to 2 and then 1. And what this is going to allow me to do is then take this true statement that I have up here at the top and this true statement that I have right here and just add them together. So if I have a sum from k equals 1 to 100 of k, and I add it to another sum from k equals 1 to 100 of k, I should have 2 sums from k equals 1 to 100 of k. And if I term by term add all of this together, 1 plus 100 is 101. And 2 and 99 is 101. And 3 and 98 is 101. And every single pairing of all of these is all going to be 101, all the way down to these last couple here. 99 plus 2 and 100 plus 1 are both 101 as well. And so we can see now that 2 of this summation from k equals 1 to 100 of just k should be 101 times however many of them there were. Well, we had the numbers from 1 to 100, which means there ought to be 100 of these. And now if we divide this by 2 so that we're just left with the sum from k equals 1 to 100 of k, that ought to now be 101 times 100 over 2 is 50, which is just 5,050. That's a pretty quick, easy, straightforward way to sum together a whole bunch of integers. So let's take the arbitrary case where we're looking at the sum from k equals 1 to any arbitrary value of n, where we're summing up the values of k, or summing up the integers. This would then look like 1 plus 2 plus 3 plus all the way up until we got to the value before n, and then the value of n. And if we did the same thing we did before, we'd say, the sum from k equals 1 to n of k could just be the same as n plus the number before n minus 1 plus the number before that, which would be n minus 2. And all the way down until we got to 2 and then to 1. And as we add these all together, we've now got 2 sums from k equals 1 to n. Well, the first couple of terms here, the n and the 1, and adds up to n plus 1. N minus 1 plus 2 is going to add up to n plus 1. And every term along the way is just going to add up to n plus 1. And if we think about this, how many n plus 1s did we have? Well, we had the integers from 1 to n, which would be n of them. So 2 times the sum from k equals 1 to n should equal n times n plus 1. And we could then just divide by 2, giving us the sum from k equals 1 to n of k is n times n plus 1 over 2. And this is a formula that you'll want to have memorized. It's a useful formula for lots of things in math, but generally speaking, today it's going to be important for us with evaluating. We have one more other important formula that's good for us to know, and that's the sum of all of the perfect squares. Right, so we have the sum from k equals 1 to n of k squared. Effectively, that means, well, we're doing 1 squared plus 2 squared plus 3 squared, all the way up to n squared. We're just adding up all the squares, 1 plus 4 plus 9 plus 16, 25, and so on. And I've given us the formula up here. It's n times n plus 1 times 2n plus 1 over 6. So we're going to go really quickly through a proof of that using induction. And so if you're not familiar with proofs by induction, they work fairly easily. The first thing that you have to do is prove that it works for the first value. So the first thing I'm going to do is I'm going to prove that this is true when n is equal to 1. So if n equals 1, this is the sum from k equals 1 to 1 of k squared. Well, that is just the first value there. That's just 1. Right? It's just 1 squared. So the question is, does that then equal this formula evaluated for n equals 1? So if we plug n equals 1 in, then we'll have 1 times 1 plus 1 times 2 plus 1 over 6. And, well, that's 1 times 2 times 3, which is 6. And if you divide that by 6, you get 1. So it works for the first value. That's the sort of the first step here in induction is to prove it works for the first value. But then after that, we've then got to prove that it being given that this works for one specific value, we can show that it works for the next value. So if we've proven that it works for 1, and we can prove that it works for n plus 1, right, then that would mean that it works for 2. And if it works for 2, and we've already proven that it works for n plus 1, then that would mean it works for 3. And if it works for 3, it must work for the next one, for 4. And if it works for 4, it must work for the next one, and so on and so on and so on. It's kind of like one domino toppling over all the other dominoes. And if it works for the first value, and we've proven that it works for quote unquote the next value, it should work for all integer values after 1. So let's say that we've got a value here where we're looking at the sum from k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 all over 6. Right? That's what we've said is true. Now, let's talk about what would happen if we instead went to n plus 1. So this is the sum. This is from k equals 1 to n. But if I add the next value, let's add the next value. So I'm going to call this over here. The next value should be, well, if I got to n and I went to the next value, that'd be n plus 1. And the way we find these numbers is by squaring them, because this is the sum of the squares. So what we've now got here is a sum from k equals 1 to n plus 1. It should be equal to the value that we knew was true plus the next term. And then the question is going to become, does this actually equal the sum from k equals 1 to n plus 1 of k squared? So effectively, if I go into my formula here and replace the n's with n plus 1s, going one term beyond, is this value equivalent to what I get from the formula thing? So that formula would then look like, well, instead of an n, I'll now have an n plus 1. And instead of an n plus 1, I'll have an n plus 1 plus 1, or an n plus 2. And instead of a 2n plus 1, I'll have 2 times n plus 1 plus 1, which will be 2n plus 3. We're going to put that all over 6. And so now the question then becomes, are both sides of that equivalent to each other? So let's throw up another page here so we have a little more room. Question is n times n plus 1 times 2n plus 1 all over 6 plus that n plus 1 squared equal to what we had on the previous page, which was supposed to be a question mark. Good looking there. N plus 1 times n plus 2 times 2n plus 3 all over 6. So on the left-hand side, we're going to need to distribute all this stuff out. So n times n plus 1 is n squared, and then plus n. And then we got that times 2n plus 1 all over 6. And then if I distribute this out, this will be n squared plus 2n plus 1. And I'm going to just get that a common denominator right now. I'll multiply by 6 over 6. And then over here, we're going to have to distribute this out. So we'll do the first two to begin with. That'll be n squared plus 3n plus 2 if I multiply n plus 1 by n plus 2. And then we'll still need to multiply that by 2n plus 3. And we'll have it all be over 6. And now that both the denominators for both of the the sides of my equal sign are 6, I can now just get rid of those denominators. I'm going to stop writing those because they're just, they're just unnecessary now. So now I need to distribute out n squared plus n times 2n plus 1. So 2n times n squared ought to be 2n cubed. And then n squared times 1 ought to be n squared. And 2n times n ought to be 2n squared. And n times 1 ought to be n. And if I distribute the 6 through this, I've got 6n squared plus 12n plus 6. And on this side, as I multiply these two polynomials together, the n squared times the 2n is 2n cubed. And the n squared times the 3 is 3n squared. Moving to the second term, 3n times 2n is 6n squared. 3n times 3 is 9n. 2 times 2n is 4n, and 2 times 3 is 6. And once again, I decided to eliminate the over 6. We don't need to bother with that. And now if I combine like terms, we end up here on the left with 2n cubed plus 3n squared. Plus another n squared, 2n squared, and 6n squared. So we actually got 9n squared. 12n and n ought to give us 13n. And then just a 6 is left. And then on the other side, we've got a 2n cubed. We've got 3n squared plus 6n squared, which is 9n squared. We've got 4n and 9n, which is 13n. We've got a 6. And so it would appear that these two things are equal to each other. And we have now proven that if we have one value that we know that works for this, for summing together integers squared, we can then show that it definitely works for the next one. So since we know it works for the first, it must work for the second. And if it works for the second, that means it must work for the one after that, which would be the third. And so on all the way down the line. So we're going to want to remember that formula, that the sum from k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 over 6. And we'll be using that quite a few times in the next couple of days. And so that's our basic introduction to sigma notation. We're going to have to use some of this next time once we really piece together the idea of how integrals actually work. But that's it for today.